hybrid object-based and Ambisonics rendering pipelines that they have for the business on it. These two always bring in a lot of really useful and useful information, so I hope that you're ready to digest all of those delicious foods you ate for lunch and turn that into knowledge and understanding now. Again, just like before, there'll be a QR code that's been passed around. That is to give us attendance details. You scan that, and then we'll also get a feedback survey as well. We really like and appreciate your feedback on each of the sessions each time. So please do scan that code if you have time. And there'll be Q&A questions at the end of the session as well. So without further ado,
thank you, Sally, for the intro. Hello, everyone. How's everyone today? First day of the show. Hope you all enjoy yourselves. I'm Michel Henein, and my partner in crime here, Haxton. We're going to sort of tag team here. I'm going to do the first portion of the discussion, and we'll continue with the rest afterwards. So we are presenting today a pipeline solution that we are going to be showing off in Unity. And it's a hybrid object-based between Ambisonics audio rendering solution. And I'm going to basically do a recap of what object-based audio is, and then we'll get into Ambisonics here in a bit. And the goal here is to create a format, well, any format that's rendering audio is attempting to present or create the correct audio at the listener location. We're basically trying to recreate reality. And what the object-based format does is it encodes the source sounds that are in the game, coming from as objects in the game environment, for example, or in the VR environment, both in some cases, and encoding that information from the sound source, the listening space itself, and its location in the room relative to the listener. So it's a combination of the sounds, the listening space itself. When you think of listening space, you're thinking of reflections in the room, for example, and the location of that object in the room relative to the listener. And you do this using an engine like our engine from Ambisonics called RISC-based. And what we do in that engine, and other engines as well, we propagate sound from the source object to the ears of the listener. And this includes the direct path of the sound, reflections of the sound in the environment, in a room, for example, reverb tail, and the interaction, the complex interaction of those elements together with HRTS. Now, everyone here should know what HRTS are, probably exposed to that term, so I might not touch on it other than say it's heavy radio transformations. So again, we're taking the sound source and encoding information about its direct path, reflection, reverb tail, and the interaction through HRTS. So the pros of using object-based audio is that it can really do a good job of recreating reality and simulating what actually happens. So that's a huge pro. It can be easily customized to real spaces. That's a definite good benefit there. And this is all done through basically simulating physics. So this is a physics-based approach. And can be customized to individuals through their own HRTS. As you all know, we're going to touch on this briefly, we all have individual traits about our anatomy, especially when it comes to the head, ear, shape, torso, all that, we're all different. So those individual unique differences that we have as people actually do affect how sound is rendered to you as an individual. Now, when you're exposed to, generally speaking, in VR and other formats out there, and games that offer HRTS are generally referred to as general HRTS. It's basically a one-size-fits-all solution. And that does a pretty good job for most people, but it doesn't necessarily create the ultimate experience, the ultimate sense of immersion, unless you've had your own HRTS. We're not going to touch on that today, but just putting it out there so you understand the idea of individualized HRTS being actually something that is a tool that you'll be seeing in the future, and actually currently, more solutions out there providing individualized HRTFs. So that's one of the big pros is that we can, in an object-based system, use individualized HRTFs. So here are the cons with object-based audio, or object-based rendering for 3D, is as the number of sources and reflections increase, the computational cost goes up. So it becomes more expensive from a computation standpoint. So it's something to keep in mind there. And it tends to be proprietary a lot of times with different solutions from different companies, including ourselves. We have our own version, and other people have their own version of the object-based rendering. Although this is starting to change, we're starting to see standards like MPEG eyes, an emerging format out there that's attempting to standardize object-based audio. So those are the pros and the cons related to object-based audio. I'm just going to touch on briefly what object-based rendering is. I'm just going to use this diagram to illustrate that here. As you can see, there's two viewpoints of a listener. We have sort of a bird's eye view of someone's head, and you can kind of see that around the head there, depending on the location, you have basically a different HRTF. And that HRTF is a different response of that location in space. And as you can see so this is on the left side, that's the horizontal plane. On the right side is the elevation plane there, that's showing of how basically HRTFs change depending on position above and around the listener using elevation. So in the vertical plane there are differences as well. So each sound wave comes from an object in space or an early reflection and is delayed and convolved with the HRTFs for that direction. And that's how this works. That's how object-based audio works. Is you're convolving these filters with whatever from space or from an object or a reflection. So this is, again, just to kind of show what object-based audio is. And so now that we've talked about object-based audio, I want to get into Ambisonics and what Ambisonics is all about. So Ambisonics represents audio near the listener as a summation of spatially varying functions. And basically, we're talking about a family of mathematical functions known as spherical harmonics. So it's basically a different way of representing 3D space using this family of functions, spherical harmonics. And I'm going to kind of step through what these members of the family, the functions, do. So when you have 4 members of this family, it's referred to as first-order ambisonics. 9 members of this family of functions is second-order ambisonics, 16 third-order ambisonics, so on and so forth, on up to 7th order, which is 64 members. And here's a diagram that kind of shows on up to 4th order. So first order, there's 4, and second order goes to 9. Third order includes what first and second, and then several of the other ones there in the third order box, and on up to 4th order. And here's what you need to understand is that the higher the number of orders, the higher the positional accuracy when it comes to ambisonics. So first order is a rougher approximation of sound in 3D space as compared to, let's say, all the way up to 7th order. So I'll kind of leave this up there. Yeah, that's kind of a cool diagram. Again, it just goes up to 4th order. Very interesting geometries there, how this all works. So pros of ambisonics are that the number of channels required stay the same for a given order. So if you're using first order ambisonics, it's 4 channels, and it's always going to be 4 channels. If you're using second, it's 9 channels, always going to be 9 channels, so on and so forth. And this is very, very useful for formats out there that need to have a sort of known or set number of channels to sort of simplify the amount of processing needed for those rendering channels. For example, you got platforms out there like YouTube and Facebook. You know, sticking with a particular number of channels is very useful from the standpoint of all the processing that happens in the cloud. You know, you don't want that number to sort of vary and get crazy, so you want it to be a sort of a known number to work with, and that's why rendering Ambisonics is very useful. So the other pro here is emerging formats. In this case, a current format, MPEG-H and MPEG-I is something that's in the works, and then it's also going to be supported in that as well. So some of the cons to sort of to realize here is that the ability to capture sound variation around the listener, it doesn't necessarily deliver as crisp of a source image. In fact, a lot of people tend to describe Ambisonics as a little bit more fuzzier, let's use a better word, come to it here, but maybe a little bit more diffuse is actually a better way to describe it. And it's a, you know, maybe hacky is a bit strong word here, just kind of you know, simplify a little bit that it tends to be a little bit of a hacky solution as opposed to an object-based software when it comes to specifically for the issue of distance enablement. What it looks like over speakers and headphones. So if you place the listener in the sweet spot and Ambisonics, it's realized over a set of speakers in this case. So for a symmetrical layout like what we have here, which is a first order layout, the number of speakers is actually twice the Ambisonics work. So I know there will be some confusion about this because I talked about 4 channels earlier. Those 4 channels are actually represented as 8 speakers in a symmetrical layout. So, so I hope that solves the confusion maybe people see out there with Ambisonics and how that relates to the number of channels versus the number of speakers and virtual speakers. So obviously over headphones, these speakers aren't physical, they're virtual. So you'll have 8 virtual speakers around the listener to represent a first order Ambisonic sound speaker. And for rendering over headphones, it creates a space with speakers, and we use the engine to propagate sounds in that space. So here's the important thing to realize is that each virtual speaker or real speaker, well, actually I apologize, over headphones would be a virtual speaker, is represented with a source and an HRTF. So essentially these speakers are an HRTF instance. Object-based versus Ambisonics rendering. So this is where we can basically compare here and get an idea of how these relate or differ. Object-based rendering does not use spherical harmonics. So it represents sounds as waves coming from a collection of sound objects. And you can think of this as a brute force method of involving waves with HRTFs to create a sound field. And so this can, you know, this can kind of get a little crazy. For example, something like our plugin, Real Space 3D, typically has hundreds of source directions in the form of HRTFs. And in our particular case, it's a rectangular configuration. If you compare that with, say, a first order Ambisonics sound field, that's 8 HRTFs. So again, the idea of comparing hundreds of HRTFs potentially with object-based versus 8 HRTFs with first order, you can already get a sense of, wow, this is going to be a lot less taxing. It's going to be CPU computation, for example. So as a result, object-based rendering does render positional cues more accurately than Ambisonics. But the trade-off here is that the computation, and Rod is actually going to touch on that a little bit more specifically later on in the discussion. So more thought on object-based versus Ambisonics rendering. So as the number, in the case of Ambisonics, as the number of sources grow in the environment, the representation always stays the same. So you can have hundreds of objects in a game environment, for example, in a VR environment, and it doesn't matter how many you have. You can have a few, you can have hundreds. If they are rendered in Ambisonics, it's always going to sort of stay the same in terms of the amount of resources being used, the number of channels being used. So that certainty in the size allows for convenient storage of the sound of the scene. So again, in the case of first order, 4 channels. And again, you can just easily distribute this as a single file with video, for example, or in the case of YouTube and Facebook. You know, you can sort of think of this as almost Ambisonics could be useful as a way to submix, right, or mix an entire scene in 3D in a discrete number of channels. So that's where it's very helpful. You can sort of think of it that way as an audio engineering. Here's a pictorial view of what the object-based can do versus, let's say, with Ambisonics. So again, just talking about how you can have many numbers of objects around the listener, and you can take that same sound field and represent it over just a fewer number of filters in the case of these virtual speakers in the first order Ambisonics example on the right. Now, from an accuracy standpoint, on the left you're going to get, generally speaking, a better 3D audio scene, a better 3D audio rendering, but the computational cost is going to be higher versus than what's on the right. So keep that in mind. Now, what we're sort of going to be talking about, and Rod is going to get into details of how the implementation occurred. We decided to unify all this in our plugin just through requests from customers. And, you know, there's advantages of incorporating both object-based and Ambisonics audio. So you can see in the dark black objects with the little speaker icons that would represent the object. So for example, if you're creating as a sound designer or game audio director, you know, you want to figure out a way where you can utilize object-based audio and Ambisonics together. What's the advantage of doing so? Well, the advantage is you can handle, let's say, very important sounds crucial to a player, have those render as object-based, and for, let's say, background objects or sounds that are a little bit less crucial to the player in terms of importance, you can render those as Ambisonics, and that's what we provide in our plugin, and there are other solutions that do that as well. So it's a great way to optimize the 3D audio scene, so that you can sort of use the advantages of both systems. In the case of object-based, you get a clearer, more precise location of sound around the user, around the listener. And with Ambisonics, you can still have the essence of 3D being represented, although a little less accurate. It's not really a big deal since all the important sounds are rendered in object-based audio. So using the two together is actually quite effective. And keep in mind as well, you may actually get recordings that are captured in the real world using an Ambisonics microphone, for example. There's lots of great microphones out there, Rode, which is a sound field, Sennheiser, Ambio, and others, including ours. We have our company develops an Ambisonics microphone, albeit it's a bit specialized and a little out of reach for most of us. It tends to be used in test measurement and analysis of noise and vibrations for market work that we use our tool for. It's a 64 microphone array. So it's a sphere about 8 inches in diameter, and it's quite expensive, but again, it's a very niche market for sonic too. But you get the idea that you can take Ambisonics recordings and use those in the environment. And one of the cool things about Ambisonics is that it's rotatable. The sound field can rotate, so it can head track. So that's one of the nice things about Ambisonics as well, which is something that object-based offers as well, is that it's rotatable and you can use head tracking to rotate relative to a user's head movement. So, so if you could think of a scenario here where, in a game where you can have objects that are very crucial, let's say you have gunfire or footsteps of an enemy player, something like a Call of Duty type environment. Those can be rendered, let's say 10 sounds that are most important to the player. Render those in object-based. Everything else in the scene, birds, whatever, something that's a little bit less important can be rendered as Ambisonics. And if you actually have a recording of, let's say, wind noise or whatever type of ambient recording that's actually recorded in Ambisonics. You can incorporate that as well. So you unify the object base, the rendered Ambisonics, and the captured Ambisonics, the recorded Ambisonics together. And I was actually having a discussion with a gentleman by the name of Carl Raikkonen, pointed out actually another really cool benefit of Ambisonics. It turns out that with something like reverb, room reflections, there's actually a benefit in having that fuzzier quality of Ambisonics, or that diffuse quality of how Ambisonics tends to represent audio. That can actually be a good thing in something like reverb. It's one of the sort of criticisms that you get with object-based room reflections is that they can be a bit harsh in terms of just sonically. The sonic quality can be a bit because it has it's less diffuse. Now you could actually incorporate other DSP tricks to handle that diffusion by filming some kind of noise. There's techniques out there that basically allow you to introduce sort of synthetic diffusion, but that diffuse nature is part of Ambisonics and how, just as the end result of the spherical harmonics tends to be a little bit more diffuse. That can be a good thing if you're working with reverb. So this is something to point out that I thought that was really interesting, that if you're representing reverberation, it might actually be a good thing to use Ambisonics to represent the room reflections in the environment. So again, you could use the object-based if you want pinpoint accuracy. If that's crucial to what you're doing, use object-based audio. If you want something less diffuse, or more, with more diffusion, I should say, then consider Ambisonics, and using the two together is very powerful. So I'm going to go and segue here into Rod's discussion. I'll just start off by saying that this particular pipeline was developed in Unity, and we actually have our Unity plugin available booth space that we have in the board room. So be sure to come by and check it out. We'll get into the development of that plugin and the pipeline.
Okay. Good afternoon, I'm Ron Haxton, the principal software engineer at Ambisonics. It's one of my jobs was in charge of recycling, cleaning up the office. I do that. So when we were at Ambisonics, as Mike mentioned, we had object-based audio, and we also had Ambisonics. And our plugin handles both, where we were getting a lot of feedback from users of the plugin, wondering, well, it's taken me time to set up object-based objects where I want them, and then I've got Ambisonics playing. And then when I move into a zone, I don't want to have to recreate new object-based audio along with Ambisonics. So, so how can we do this? And he was like, no, that's going to take a lot of time. I'm going to do that. I can get a lot of people coming to you, and it's like, okay, we're going to be give them what they want. So he came up with this, what I had called a combo, object-based combo, and Mike had the better mashup, so you have to get a better term. And so basically, we use, since our plugin runs in Unity, also Unreal. Unity has a baseline called a native audio plugin, which allows you to basically create threads to get callbacks to do what you want to do. So they already have like a built-in pipeline for object-based audio, and then they added in the last 2 or 3 years Ambisonics. Currently, they only support up to the 2nd order. Our engine handles 7th order, as Mike was showing me that diagram where it's Ambisonics channel numbering systems. There's a couple of formats for that I'll get into. But our plugin, also let me explain that this isn't a plug for you to use our plugin. It's just that this is how we did it, and we use Unity to do So I'll just give you a background on Unity's native audio plugin first. So they have a method where you register through eNews all the different callbacks that you'd like to get handling for these the parameters that you can get during this callback. And so basically there's like 8 values that you can set up that you then call and set your getters on. And you register, and the main callback is where the processing is. So there's you can imagine there's this audio stream coming in through the DSP. And if it's object-based, it's 2 channels, as Mike mentioned. It's Ambisonics, it's 4 channels. So first of all, let me just say this is going to get a little technical with programming. So how many developers do we have? Okay, that's good. So, all right. So as Mike was explaining, Ambisonics, the formats, basically it's the format of Ambisonics. And there's like 3 standards right now, all small. Ambisonics channel numbering, like SN3D and M3D. And these were derived from when spherical harmonics was being introduced. There were just no way to, there wasn't already a built-in way to do the formalization of this from a couple of different backgrounds. Like SN3D, I think, came from geology and magnetics and Funan. I gave it out, but N3D came, I think, from physics and mathematics. And they're all pretty much doing the same thing of trying to represent this Ambisonics sphere around your head. And so these are the 3 main ones that I think they use and some others. So now to our plugin. We have threads for the object base and threads for the Ambisonics. So we have the Ambisonics component and the object based component. And in order to do this mashup, I created another component, which is the convolver. The convolver is where the math and everything for going from object base to Ambisonics happens. So in Unity, with the native audio plugin, we got a callback for an object base, we got a callback for Ambisonics, and now we also have a callback for this convolver. So on those registered parameters, I created a flag that says, okay, this is for input and this is for output. So when the object base is getting its input, if say we have 3 spheres in the world as a representation of these audio sources, so 3 audio sources with input coming into it as object based, it has 2 channel inputs. But we want to be able to go to Ambisonics, which is 4 channels. So the convolver sits at an output that has 4 channels coming in to it. So basically, we're taking the 2 inputs into each one of our audio sources of its own thread. So the inputs are coming in, and we're taking that information of those audio streams channels, and then directing them to the convolver. And so first of all, we've got to get the listener's orientation as to where he is in the room. So this is done with returning ins, and we set up the head orientation based off of this map that allows us to know the direction that the listener is looking at. And after that, this is basically a B format of the formula, basically Ambisonics B format of how you represent the source impulse to get the weighted, and then so the X is the front, back, the Y is left, right, and the Z is the horizontal. And in our plugin for the object base, there are 2 input buffers. And these 2 input buffers are working as toggles. So while one is being worked on, we're gathering the input data, the stream, the audio stream of the second buffer. And we also have created global buffers for the Ambisonics to follow. So the data comes in and we do the math to set up an Ambisonics pen. So this is an object-based audio that's been set up as object-based, coming in as 2 channels. And now we're going to convert it over to 4 channels. And this is the process of doing it. So the length of the audio stream. We're pumping it into this Ambi buffer that I created for the Ambisonics, taking the 2 channels that you see in that M buffer, and this is basically where the beginning of the mashup happens. So they haven't set up any Ambisonics in their scene, it's just all 3D object-based audio, but on the fly, we're quickly changing it over to Ambisonics. And so our future plans for this is to also take into effect, like our object-based audio does material reflections in our room. So you can set up an environment and say, oh, it has carpet, it has tile, plaster, and we take in all of those reflections and give you the actual acoustics of that room. And right now, Ambisonics doesn't do that, it doesn't handle that, but we can actually do it with our engine since we already know from these 3D objects what the room environment looks like. And that's one thing I forgot to mention is that our object-based audio is still rendered in what we call a shoebox environment. We are working on right now, and it should be coming out soon, where we can do arbitrary geometry rooms. But right now, we're in shoebox environment. So with that same shoebox environment, when we switch over from object-based on the fly to Ambisonics, we can easily incorporate those material reflections and give you the same output of what you're doing in object-based. And the reason that this approach works is because object-based audio, as Michael mentioned, extremely computational. And so I'm going to show you a demo where we're putting up object-based audios, and at a certain point of however many objects I've been in, you'll see where our engine starts to break down, and you'll start to hear degradation. But then if I switch it over to Ambisonics, you get a whole lot more objects into the scene. So So this is a demo. I'll bring the profile so this you can see what I mean. Here's the component that I mentioned involved. So basically, in our plugin, we've got a couple of components where we have a listener and we can set up one here for Ambisonics. These three formats. I think Unity defaults to ACM, SM3. Our default is Fluent, but you can switch it in our plugin. And this is the Ambisonics default. So you have to put this in the screen if you want to do this combo of representation. And I'll just quickly show you. The audio source, you can, like I said, we can do regular 3D spatial sound and play Ambisonics, we can set it up to do Ambisonics. So I already have some prefabs in here that I'm going to run and show you this demonstration. So first I'll put in the object-based audio.
It's just coming out into. Is this the loop?
that you can see is that if you want to do object-based also, you don't want to have to set up your scene, you know, like, oh, I want these objects to be spatialized, or even though I want these characters in the scene to be Ambisonics. You know, you can just set this up to be object-based, and then
Sorry.
But what we're trying to figure out now is, sure, we can change them on the fly, but we're not sound designers or sound directors, and we're trying to get feedback on where we should start switching, you know, doing the switch of how we want this to work. This, you know, be able to determine these, when should we switch from object to science. And we can arbitrarily, you know, say, oh, when we get to this certain range, you know, we'll switch to as a